Hello, today we shall learn in this lecture the polarization of light, its meaning and types, method of polarization and its application. So let us start with some examples. Here there is no problem with these pictures. If so, then what about them? The previous pictures were taken without polarizer and the later are with polarizer lenses. Here the better color saturation and darkened sky are achieved. Here also these pictures are taken without polarizer and these are taken with polarizers. Here also the polarizers are used to dehaze the view. These pictures are also clear, but these are amazing. So difference is clear with polarizer photography. The polarizer lenses can be used in underwater photography also. The polarized lenses are used to reduce sun glare, reflection and haze, and to increase darkness of sky and color saturation. In modern theory, light is produced when an excited electron in an atom returns to its ground state, and in doing so, it releases its extra energy in form of photon. Once the electron has come to its ground state, the emission of light is stopped. Now another wavelet gets emitted by another atom by de-excitation of electron. Therefore, a light beam is composed of a large number of small wavelets emitted from different atoms at different times. All these wavelets are independent of each other, although they are traveling in the same direction. Please note here that although light has magnetic vectors also, but we shall talk about electric vectors only. The reason is twofold. One, the amplitude of magnetic vector is very small with respect to that of electric vector. So the illuminating effect of light is due solely to its electric vector. And the second, the magnetic vector is always perpendicular to the electric vector. So there is no need to talk about magnetic vector if electric vector is talked about already. So let the first wavelet is emitted and it is traveling along z direction. This is x-axis, this is y-axis. The vibrations of electric vectors are suppose along x-axis. The another wavelet is emitted now. The electric vectors of this wavelet are not bound to vibrate along x-axis, yet they are vibrating along y-axis. Similarly, the electric vibrations of different wavelets are all perpendicular to the direction of propagation, but they are in different directions with respect to each other. Therefore, an observer placed here will observe that electric vectors are vibrating in all the directions, perpendicular to the direction of propagation. This type of light is known as unpolarized light. The light which we get from any natural source of light is unpolarized. Therefore, a polarized wave is the one which have electric vibration along a single direction perpendicular to the direction of propagation of light wave. And the polarization is possible only with transverse wave. Here you see that the transverse waves in a rope can easily transmit through these two slits if the cut of these slits are along the direction of vibration of the rope. If the second slit is rotated to make its cut perpendicular to that of the first slit, then we cannot get the wave on the other side of the second slit. It is clear that if the wave in the rope is longitudinal, then above phenomena will not be observed. So the polarization is possible in transverse wave only. The similar phenomena is observed with light wave also. Here we have two polarizers in place of light path. These. We shall study more about polarizers in next slides, but for now we can consider a polarizer as a plate which allows a light wavelet through it if the wavelet has vibrations of its electric vectors along a particular direction. This particular direction is known as axis of transmission of the polarizer or the optic axis of the polarizer. If the directions of transmission axis of both the polarizers are parallel to each other, the light on the other side of the second polarizer is found. If any one of them is rotated to make their transmission axis perpendicular, then no light at the other side of second polarizer can be found. This shows that light wave can be polarized. And it is polarization of light waves which proved that light is not longitudinal, but it is a transverse wave. In this, you can see two polarizers. When they are placed such that their transmission axes are parallel to each other, light can be transmitted. But if any of them is rotated by 90 degree, no light can be passed. In a polarized light wave, the plane in which the electric vectors vibrate is known as plane of vibrations, and the plane in which the vibrations of electric vectors are suppressed or removed is known as plane of polarization. So the plane of polarization and the plane of vibrations are perpendicular to each other. The polarization can be classified in three classes, namely linear polarization, circular polarization, or elliptical polarization. The polarization which we have studied till now is linear polarization. There will be no difference if two orthogonal linearly polarized light waves with same phase are superposed. As the electric vectors add vectorially, this will be the plane of vibration in the resultant polarized light wave. So, two orthogonal plane waves with same phase but possibly different amplitudes give the linear polarization. And what if two superposed linearly polarized waves are not in phase? Like this. Here, these are two linearly polarized light rays, but there is a phase difference between them equal to 90 degree. Then, the resultant electric vector will be rotated as the light propagates. As this resultant light wave will be observed by an observer, the observer will see as the electric vector of the light is rotating in a circle. This type of polarization is known as circular polarization. Therefore, two orthogonal plane waves with 90-degree phase difference and same amplitude give the circular polarization. And what if the amplitudes are not same? In this case, the observer will see as the electric vector of light is rotating in an ellipse. This type of polarization is known as elliptical polarization. So, two orthogonal plane waves with 90-degree phase difference as well as different amplitudes give the elliptical polarization. So, these are methods of getting a polarized light. So, we will discuss them one by one. The wire-grid polarizer consists of a large number of thin copper wires placed parallel to each other. The physics behind the working of the wire-grid polarizer is probably the easiest to understand. When an unpolarized light wave is incident on it, then the component of the electric vectors along the length of the wire is absorbed. This is so because the electric field does work on the electrons inside the thin wires, and the energy associated with the electric field is lost in the Joule heating of the wires. On the other hand, since the wires are assumed to be very thin, the components of electric vector perpendicular to the wire length passes through without much attenuation. Thus, the emergent wave is linearly polarized with the electric vector perpendicular to the length of the wire, like this. Therefore, if a linearly polarized light is incident on a wire grid polarizer, the output will be most intense if the plane of vibration is perpendicular to the wire length. The output will be least intense if the plane of vibration is parallel to the wire length. However, for the system to be effective, the spacing between the wires should be less than the wavelength of the light. The second method of polarization is polarization by reflection. In this method, if an unpolarized light wave incidents on a transparent medium on a specific angle of incidence known as Brewster's angle or angle of polarization, then the reflected light is fully polarized. The vibrations of electric vector in the reflected light are parallel to reflecting surface. The reflected or transmitted light is partially polarized in this case. The Brewster's law says that tangent of angle of polarization alpha is equal to the refractive index of the medium. Further analysis proves that in this case the sum of angle of polarization and angle of refraction is 90 degree. Or in other words, the Brewster's law says that the reflected and refracted waves are perpendicular to each other. Therefore, in daytime, when sun comes at position in the sky so that angle of incidence of its light rays on earth is equal to Brewster's angle, then the reflected light from earth or water surface is polarized horizontally. Because the reflection coefficient of any surface is very less, so the amount of reflected polarized light is very less. So a pile of parallel glass plates can be used to increase the intensity of reflected light. As a function of number of parallel plates, the intensity of reflected light is plotted here. This. The plot says that initially with increase in number of reflecting plates, the intensity of reflected light increases sharply, but later on the graph gets almost saturated. Therefore, it is seen that the pile of around 24 plates can make 90% of the incident light polarized. The next method is polarization by selective absorption. It is also known as dichroism. In nature, there are some materials, the crystals or solutions of which can absorb one or two plane polarized components of transmitted lights more strongly than the other. This property is known as dichroism, and it is the basis for the formation of polarides. So, to make a polaride, microcrystals of any dichroic material are first aligned with their optic axis along one direction, and then they are joined together in form of a sheet using a fast drying material. When the sheet is sandwiched between two thin glass plates, a polarized is formed. In the examples, you have already seen the applications in polarization photography. There can be many applications of Polaroid. Like in anti-glare sunglasses, the Polaroid lenses with vertical transmission axes are used, which can filter out the reflected polarized light with horizontal vibrations or glare. In automobile headlights and windscreens, the Polaroid with transmission axes inclined by 45 degree with vertical axis are used. When a windscreen comes in front of headlight, the transmission axes of them become perpendicular to each other to block most of light from headlight from entering the windscreen of the vehicle. Mary's law says that the amplitude of polarized light passing a polarizer is directly proportional to the cosine of angle between plane of vibration of polarized light and transmission axis of the analyzer. Or in terms of intensity, the intensity of polarized light passing an analyzer is directly proportional to the square of cosine of angle between plane of vibration of polarized light and transmission axis of the analyzer.